Okay, so you got your two variables project here. Okay, I'm just going to get some stuff in here. There's a lot of reading to go on here. We can do a lot of the reading together when we get back to class, okay? But this is giving you a little template for your maths studies project, which you'll eventually do your internal assessment. So let's get to it. I've got the alcohol versus GDP, and so there's my graph. I've got it there. Now, technically, it's a bit naughty here to have this. We did the line of best fit so we could see what the R value was, the R squared here, and then we all compared, didn't we? The R squared value that we got from a massive table of data, you know, with the SX, the SY, the SXY, and then the R. And then I just squared this value down here to get my R squared value. So this is 2.6 times 10 to the negative 3, and this here is 2.2 times 10 to the negative 3. So there's slight differences here, but I'm not too worried about that. Technically, this is zero correlation. There doesn't seem to be any link between GDP per capita and alcohol consumption, which I thought there might be. You know, I thought that maybe poorer countries led to higher rates of alcoholism. Okay, it doesn't seem to be the case because it's got a very, very low R squared value, and actually a very low R value. Remember, greater than 5 is, you know, something that we're looking for if we think there might be a connection. So I really should go back to this graph, and I should not have that graph with a line of best fit on. Because if you draw a line of best fit on a graph, it means you're going to use it to make predictions. Now, how can we make predictions if there's actually no link between the two variables? So let's get rid of the trend line. Okay, and I'll also get rid of the legend. Okay, update. Great. So I'm just going to copy that graph across. You can actually screenshot it or just paste it. I'll screenshot it so I can get a nice bit of a clean list to it. Data, diagrams. Draw the scatter graph. So I'm just going to put it under here, and I'll just tidy up later. But I am actually going to put this as figure 1. Okay. You can, if you want to be really scientific, let me just do this again. Oh, figure 1. Oh, there's a scatter graph gone. There it is. And there's figure 1. You can actually put a full details here. You know, you could just say scatter graph to show the GDP per capita US dollars, purchasing power parity, inflation adjusted, a lot of good detail, versus alcohol consumption, I think is litres per person per year in 36 randomly sampled countries. There you go, so that's really a full description of what that graph is. In that case, we actually probably don't even need the title of it because we've got all the details here in the figure 1 here. One of the conventions is you can label everything as a figure, even if it's a table of data or a diagram or a graph. We can call them all figures, and then, yeah, you don't have to worry about that. So there's figure 1, that stays nicely together. Great, so I'm going to look at some more diagrams here, okay? Now, I'm going to look at the individual variables. I'm going to look at the GDP per capita for countries and just have a little look at that data on its own, yeah? So down here, I'm actually going to draw a histogram for just the GDP per capita. So I'm going to take this data here, all these countries. So Command C. I'm actually going to get my TI Inspire out. I've got a spreadsheet all ready for it. Click on the top one, little paste, they're all in there. So this is GDP, and I'll do it for GDP, then you can also do it for your other variable. Doc, insert data and stats. So this is GDP, isn't it? See, that's got a nice little dot graph, hasn't it? Nice little dot graph, okay? So now menu, plot type, histogram. It's kind of cool, isn't it? Yeah. So the histogram and these kind of bars here, these are from 0, okay, look, 0 to 5,000, 5,000 to 10,000. So they go up by 5,000 widths, okay? If you want to change those, and you can do, menu, plot properties, histogram properties, and you see the bin settings. So equal bin width is what we've got, which is great. Now we go to the scale, percent and density, great. So let's go back to the bin settings. I'm going to go equal bin width, and the width I'm going to change to 10,000. Now look, it starts at 0. See that? And I can grab the frequency here. It's kind of nice, isn't it? Yeah. So that kind of makes sense. Okay, see that picture? So this data is not normally distributed, is it? Yeah. That normal distribution would be a nice little mound in the middle. Okay. This has got a lot right there. A lot of countries with a small amount of GDP and a few with a big amount of GDP. Okay. So I'm going to take a screenshot of that and put it in. This is just data I can add to my. Let's go back to my. There we go. Okay, now this could become my figure 1 here, so I need to be working that out. So that's quite nice. And I'm just going to see if there's any outliers in the data. Now, outliers, data points that lie a long way away from the mean and the median. So I'm actually going to do document, insert yet another data stats, and now I'm going to do the same GDP. I'm looking at it a slightly different way. I'm going to look at it as a menu, plot type, and I'm going to look at a box plot. And there we see those are our 3 outliers. Yeah, so the ones that are just drawn as dots on their own indicate outliers. They lie so far out of the kind of spread of all the other values that they could be considered to be outliers. Yeah, so that's just quite interesting, isn't it? That we could actually say that. Let's get this one here. Could say that these 3 countries act as outliers. Now, the interesting thing, I suppose, is if we go back to our graph here, these 3 points here, over 60,000 is considered an outlier. Yeah. So why don't we do something a bit cheeky? If we go back over here and find out all the ones over 60,000, and actually if we deleted them, so it's this one here, this one, and this one. So if we just go ahead and delete these, let's see what happens. It's pretty cool, eh? Yeah. Now I'm just going to adjust this because this was a count of 36. Let me just drag it across. Now all my figures here should automatically adjust. It's pretty good, eh? But this is 36, 36, this is 39, 39. But actually, if I move these 3 countries here, there shouldn't be anything in here. So let's just get rid of all of that. Fantastic. Do you see all my R values change? Now look at my R value now. It's gone up to 0.33. Do you remember what it was before? Yeah, it was like 0.02. So by removing 3 outliers, I've suddenly got a big change in the R value. It's still not greater than 0.5, but the removal of outliers seems to, allow the data to fit better a straight line. So now it would make a little bit of sense to fit a straight line through here. But again, look, it's so spread out, and the value here is 0.33. Yeah. So that's got a little tip that you could have. That's how to identify outliers. We identified outliers by looking at the box and whiskers plot, and anything in the little dots here are outliers. So that's just a top tip. So if you do nothing else for the homework, then just do those little tricks. If you want to do any more on your Google document, you can do. You can fill it in a little bit more and start to think about all the other pieces. That would be absolutely great. There's no problem with that. I'm going to show you one more trick though here, because I think John in class saying, well, do we have to fit a line of best fit? Now, this big spreadsheet doing all these fancy formulas here and the SX, SXY, this is to work out the R for a line of best fit. It's only for a straight line. But the computer can fit any kind of curve. It can fit an exponential curve, one of those growth ones. It can fit actually a quadratic as well if you want it to. If you think there's a justification for a quadratic here, then you could try and fit it. Now I am actually going to try and justify why I think a quadratic might be a good fit. So listen to this reasoning. If I draw a quadratic that goes kind of up here and then back down here, how might I interpret the model? Yeah. So it says that as GDP per capita rises, alcohol consumption per person rises. Now, does that make sense? If you've got more money to spend, you might purchase more of everything, so therefore you might purchase more alcohol. So that would kind of make sense, yeah? But then maybe it gets to a certain limit that actually, if you get to a certain GDP per capita, you've kind of maxed out at how much alcohol you want to buy, then maybe beyond a certain GDP per capita, education and understanding about the downside of alcohol kicks in. So the richer countries get, the more educated and aware they become about alcohol, and maybe alcohol consumption starts to decline again. So for me, this kind of upside down quadratic might make sense. It might actually be a good explanation for this pattern of data. So let me just go for it. Advanced edit, customization down here, trend line, polynomial. Okay, so it looks to it sort of fit a quadratic, degree 2, yeah. Could change it to cubic, but I'm going to fit with a quadratic for now. I will put the r squared value in, and I want label is use equation, and I don't see it appearing here because I haven't got the legend sorted out. So if I put up here, legend right, that's great. And let me just go back down here again. Show r squared, that looks alright. Use equation, polynomial, that seems to have fitted really nicely. I just wonder if all of this is in. Have I got details here? Yeah, let's try that now. Okay, cool. Now look, the r squared value is 0.392. And look at the fit here. It looks quite good, doesn't it? Yeah. So if the r squared is 0.392, let's think about what the r value is. So in here, 0.392. And in here, that's the r squared value, r hat 2. So if I want the r value, I've just got to square root this guy. So equals this to the hat 0.5. Oh, look at that, the r value is 0.63. So all of a sudden my data here has got a strong correlation. Now this is the r value of 0.63, yeah? So if we can use if you can use r values for quadratics in the same way as we can for linear as a comparison, this is quite a big value, yeah? But actually, technically we can't use the r value for anything other than, that's my alarm going off, for anything other than a straight line, yeah? So now for anything other than a straight line, we need to look at the r squared value, yeah? So the r squared value is 0.392, and do we think that's quite a good fit model? Now we have to have some kind of scale for r squared values, yeah? So for r values, we said that 0.5 and above would be, strong positive correlation. So how does the r change into r squared? R squared equals 0.5 squared, 0.25. So anything above 0.25 is a strong positive correlation, or just a strong correlation, a strong fit for the model. Our r squared value is 0.392. So this is a good model, and one we can actually use to make predictions.